Hey guys, today we are going to talk about Standard 5. Standard 5 says carrying capacity and homeostasis within biomes can be explained using mathematical graphing and algebraic knowledge. Carrying capacity is defined as the population equilibrium size when births and deaths are equal, hence population growth equals 0. So based on the standard, hopefully you can recognize that this is going to build quite a bit from standards 3 and 4. So we still need that idea of ecosystems from standard 3. Remember, an ecosystem is a collection of all the living things in an area called the community, plus the abiotic or non-living factors that they interact with. So we still have those ecosystems. We're also now looking at biomes. Remember, biome are just collections of ecosystems that are super similar. And again, we're saying that those biomes, so those ecosystems, are in equilibrium or what we call homeostasis. So homeostasis is just another term for equilibrium, meaning it's this constant kind of set standard for everything happening in the biome. So at homeostasis, your population sizes are stable, they're not changing. All those things we learned about in standard 4, competition, all of that is staying at a regular rate. So that's homeostasis, just equilibrium. And we're also continuing to talk about carrying capacity. So hopefully you remember from standard 4 that carrying capacity is the maximum number of individuals of a species that can live in an ecosystem or in a biome, whatever we're talking about. So again, in this standard, we're seeing that you can actually calculate whether or not an ecosystem is in equilibrium using math. So we can calculate the carrying capacity. And if the population is in homeostasis or in equilibrium, then the number of individuals being born will equal out to the number of individuals that are dying. So if the population can handle 100 rabbits, then they should be being born and dying at the same rate. If those numbers are not equal, that means the population is not in equilibrium. Something's changing because the population size is changing. So the growth rates should be 0. If that growth rate is 0, again, the population is not getting bigger or smaller, then you know you're in equilibrium. So you can look at a graph of the number of individuals in a population over time. And you can see this is a graph estimating number of deer of a population over the years. And you can see it's going to go up and down. It's kind of cyclic, but you have this carrying capacity kind of right in the middle. It's almost like the average. So if it gets too high, then the number of deaths is going to get bigger than the number of births to bring it back down to that carrying capacity. If it gets too low, then the birth number will increase so that we can increase that number of population. And the reason that the carrying capacity is set where it is because of a limiting resource. So there's all kinds of resources living things need to survive. There's typically one or maybe more than one resource that's limited. So it could be space for trees. There's only a certain amount of space. If there's too many trees, some of them will die. It could be prey, so what they're eating. It could be water. But there's something that will limit the population size. So it's the thing that sort of keeps the number down to what it is, down to that carrying capacity. And so what ecologists will do is they'll try to find what the limiting resource is based on the population they're talking about. And again, we can use that mathematical evidence of equilibrium to figure out what the carrying capacity is, which helps us to identify the limiting resource. So if we look at a graph here, you can see that if the population size isn't changing, technically we'd have a straight across line. But because this is reality, this is ecology, it's real life living things, it doesn't exactly work like that. So a population in equilibrium will kind of look like the other graph. Again, there's ups and downs, but it's sort of cycling around this general average of the carrying capacity. So you can kind of see if you impose those graphs on each other, that straight line would be sort of the average of the peaks. So that's kind of what a population would look like in equilibrium. But we can also do the math to see a population not in equilibrium. It would look a little bit more like this. So you can see that in years 1 through 3, the population size, whatever we're talking about, was much higher than what it was years 4 through 8. So there's something that happened between the measurement of year 3 and year 4 that changed the population size very drastically. So something happened there. Again, think back to our last standard. It could have been a drought. It could be humans starting to hunt them. It could be whatever limiting resource, though, changed. and the population size got drastically lower, and it sort of made a new carrying capacity. So you can see here the population is getting back into probably an equilibrium, although it's not really clear, right? Because we have this graph that's going up, so maybe it's trying to get back up to the size of the population in year 3, but again, it's trying to reorient itself based on the limiting factor. So again, in equilibrium, not in equilibrium. So what we'll do with this activity is we're actually going to be a population of deer, and we're going to have limiting resources, and we're going to see what happens to the population size. So again, this standard is all about how we can use graphs and math to actually calculate carrying capacity and actually calculate whether or not an ecosystem is in equilibrium. So let me know if you have any questions, and good luck.